group here. And so it's joint work with my collaborator, Burak Çakmak, who is here. So this book is related to machine learning, but it's not about neural network learning, although we will see that some of the results have a flavor of neural networks, so it might also be interesting for people who are interested in deep learning or recurrent neural networks. So I have to say I don't know, I'm not a real machine, well, possibly now I'm a machine learner, but my background is in statistical physics, and so a lot of the things that I'm doing are related of ideas that have originally come out of statistical physics. And so I will spend the first part of my talk to do a little bit of motivation, explaining where this has to be embedded, and I will talk about something, as I said, neural network. It's not neural network learning, but something that other groups in machine learning do, and it's called probabilistic inference. And you have to do certain computations there, and some of the approximate computations have actually a background that comes from the cavity method, which has been introduced in several talks before. And a very specific problem that we're going to address is something, fixed point equation coming out of the cavity method. They are known in statistical physics as TAP equations. So I will restrict myself to a model that we can really analyze in detail. Unfortunately, it's not yet a real data model, but we hope that from there we can go on to more interesting models. So we stick to a specific Ising model, and then discuss the specific EP algorithm for solving these equations, and then we'll have a recurrent type of network dynamics. So after that motivation, I like to present the analysis of this algorithm dynamics, and we use a specific technique that has been used in statistical physics of disordered systems. It's called the dynamical functional approach, and for this type of problem, we are able to find explicit solutions and compare them with simulations. And if I have time enough, I will also try and see what a little bit of an understanding of the results, and show that how, in what sense they are robust by making a few less specific assumptions made in our analysis. Okay, so probabilistic inference, it's a method where we model data y and sort of hidden variables that we don't know by joint probability densities, and we compute conditional distributions of the things that we do not know, given the things that we observe. So this is just Bayes' rule. And the problem in practice for these models, if these probability distributions are non-Gaussian or non-factorizing, then we have the problem of actually computing, for instance, the denominator, which would be a high-dimensional integral, usually if x is a high-dimensional object or a sum. And we would also have similar problems if you want to make predictions on a single xi. We would have to marginalize out all the other variables, so that means an integral x without variable I, so ixi is kept fixed. And so it's a problem of do high-dimensional sums or integration. So it's a typical problem that we face in statistical physics. And a specific class of models, which is, I would say, it's fairly common, and it's highly non-trivial. You would consider these kind of things that we often call a Gaussian latent variable model. So it has like a part that looks like a Gaussian. So these variables xi and xj are coupled by this matrix Kij. And here we have something, sort of terms that are defined on single sides. And they are usually of non-Gaussian type, and we would have to do certain non-Gaussian computations. And so examples would be, for instance, things that are related to probabilistic classifiers. So these kind of things, so this kind of thing, maybe the inverse covariance matrix of a Gaussian process. And if we would introduce likelihood terms that are related to sigmoidal functions, then you can view them as kind of a probabilistic classifier. Other applications would be, for instance, the field of compressed sensing, where you assume that your data are obtained by a matrix H applied to the vector X to be estimated. You add some Gaussian noise. And so that would lead, if you have this Gaussian noise model, would lead to a quadratic expression in X. And if you now impose a sparsity prior distribution that enforces a variety of
sorry, what is
you don't know which one, a variety of these elements to be actually zero, then you would end up with a problem that is again of this kind of thing where F is not Gaussian. And now of course, my favorite model as a physicist that also falls into that class is the simple Ising model. And so you can put them in the same class. We have discrete string variables. Okay, the convention is we put a plus rather than a minus sign here, and we were just simply taking a sum of delta functions that are concentrated at plus or minus 1 to fit it into the frame. So I will usually think about this model, and of course it doesn't have really to do with data. You could say, well, look, these external fields might be related to observed data, but I don't want to make this kind of discussion now, but just study these kind of models, let's say for fully connected matrices Jij. So the question is now, how can we make inference with these kind of models? And there's a group of ideas that comes actually out of the cavity approach, introduced by Mirza Parisi and Virasoro. So the idea is if we're interested in the distribution of one of the ith component of that vector, so we can write that in a simple way. We take one of these factors that corresponds to xi. We take the internal field that's coupled to xi, and here is the distribution of the remaining variables that are not equal to xi. So it's the question, how can we marginalize out these other variables? And the idea would be, we know already if we have a sparse graph, then we can think about, we could have this idea that we have a tree-like structure and think about factorizations. But in the other limit, we have a dense graph and let's say small couplings. We could say, look, I mean, what we have to do is we would write down the joint distribution of the variable xi and the internal field acting on xi, so it would be that, and we would need the field distribution, which is something like that. We integrate over all variables, xj, when we take xi out of the system. And the idea would be to say, look, approximately for a dense system, we could assume a kind of a central limit theorem and say this, we approximate that field by a Gaussian. So that would be the simplest approximation for a dense system. We would say locally we have a Gaussian with a mean AI and a variance VI, and then we can immediately integrate out that field and get an explicit result for this marginal distribution. Of course, the problem is we have to sort of come up with an algorithm that self-consistently computes AI and VI from the magnetizations in the problem. So yes. Yes. Okay, so one thing is easy to do within this Gaussian approximation. It's easy to relate the cavity mean, so it can be written in such a way. So the only non-trivial part is these cavity variances, and a very simple approximation would be completely neglect dependencies. So this VI is by definition the variance of these cavity fields, and if we make this approximation, then we would end up with something that's known in the statistical physics of spin glasses as the TAP equations given by Thales Anderson and Palmer in 1977. So it's a self-consistent a set of equations for the magnetization of such a model, and it's believed to be correct in the high temperature phase of the model, of the Sherrington-Kirkpatrick models. That is, for a system where the Jij's are just Gaussian couplings where the variances are scaled down by n. So this is the simplest kind of thing, and so we were motivated by these kind of ideas to come up with this with so-called adaptive TAP equations together with Ole Winter, and we used an idea that we learned from a paper of Giorgio Parisi and Mark Potters in 1995, which says it's a good assumption that these cavity field variances should only depend on the moments, on the first and second moments of these variables. Well, for spin systems, it's just the one here, and do not. So this dependency is not specific on the model that we have. So we can then get this relation if we actually study a Gaussian model where these non-Gaussian terms are replaced by Gaussian terms. And in this case, we get a set of equations that actually relate Gaussian variances to cavity variances. So this is a little bit the story. So at the end of the day, it gives you a system of self-consistent system of equations that have to compute, that allow you to compute approximations to the mean and the variances of such non-Gaussian models. And the problem is, you already see, well, it's a system of nonlinear equations. I'm not writing it down. You can see it in the transparency in a couple of minutes. So you have to somehow solve them in an efficient way. Actually, we, Ole Winter and myself, we haven't really looked into that. We said, okay, maybe some solution by iteration, but independently from a completely different perspective. Tom Minka, essentially in the same year, came up with an inference algorithm that he called Expectation Propagation, and found out that his result is actually the fixed point of his algorithm solves precisely these equations, and so nowadays we stick to EP, expectation propagation. And for systems that are not too large, we can compare actually the outcomes of this algorithm with Monte Carlo simulations, which would give us the exact answer if we run Monte Carlo long enough. And typically, we get very good results for these approximations. And there's a website run by Tom Minka. I think it's not quite updated, but it has a large bunch of applications of these techniques. So what's the disadvantages? The disadvantage of the technique is that the variance updates are really costly. So in all these message passing kind of things, we have to do sort of matrix inversions. We can replace them in practice by rank 1 updates, but the problem is still it's the complexity of this kind of thing. And the other argument is we don't know much about convergence. So it seems if it converges fast, you get good results, and there's all kind of ideas. If it doesn't converge, you shouldn't enforce it to converge because possibly the results are not quite okay. So it's a little bit. There's not too much really understood, and I think this is something that people don't like because it's not a standard kind of gradient descent algorithm, which are now very popular. Gradient descent, stochastic gradient descent, or something like that. It's a nice parallel or sequential algorithm, and we don't know much about what's going on. So it's a question.
Is it a bit like a belief propagation?
It is some sort of a belief propagation, but not for sparse, but for dense matrices.
Okay.
Yeah. So what we propagate is essentially first and second moments of certain distributions. So that's why it's called expectation propagation. Certain expectations are propagated in the system. But it has the same flavor. So the question that we try to address is, can we simplify EP, this expectation propagation, to deal with these problematic matrix inversions, and also can we try and understand typical properties of the algorithm? and hopefully we can do something for large systems, and if we would make random matrix assumptions for those couplings. The question, of course, in practice will be, are real data like that? We have to see. This will not always be the case, and hopefully in certain cases it will be the case, but let's say that's the kind of game that we try to play. And of course, it's related to other results that people, for instance, have addressed, for instance, in the field of compressed sensing, where people have looked at specific algorithms that are known as AMP, approximate message passing algorithms, and there's a variety of results that people have obtained for specific distributions. But I think in our case, it's a different story. We're not just interested in plain how well will the algorithm approximate the problem that we want to solve, but we really want to see, can we actually say something about the complete dynamics independently of if this solves really the problem that we want or not, but we want to understand the full dynamics, including rates of convergence. Okay, so one comment about the costly variance condition for the second moments. So within the expectation propagation algorithm, we have to repeatedly solve the problem that we have non-negative numbers chi-i. So this is the variances that come out of the local computations. That would be 1 minus the magnetization squared in case of an Ising model. But we would have to find a diagonal matrix lambda such that this equality is there. So the interesting thing is, just briefly, we want to see, can we do something? Can we solve this approximately if J is a random matrix? And when we mean a random matrices, we will study random orthogonal ensembles where we say, okay, we can split J into this rotation, and D is the diagonal matrix containing the eigenvalues. And so we're assuming that O and D are independent, so we essentially care about the eigenvalues, but assume that kind of the eigenvectors are in general position. That is, of course, the approximation, and if sort of data would not obey that, it would be another approximation, but maybe not one that is completely lethal. Right, so in this case, we can do something. We can actually show that this is the solution of the following problem. So this lambda matrix, so this diagonal matrix, where this is the so-called R transform of the matrix J, and I don't have time to define R transforms, but it's something, for those who don't know, that is characterized by the spectrum, the limiting spectrum of the J matrix. So we get an explicit solution to that computation in the sense that this converges to zero. So the difference between the two squared summed and normalized converges to zero. So this is one of the simplifications that we make, and we already learned that this is that was had been already used in the statistical physics community by Parisi and Potters, and they then wrote down the fixed point equations for the approximate magnetization in the following form, where this chi is a scalar quantity, and you have to solve this nonlinear equation. So this is the kind of fixed point equation for the random matrix TAP problem, and now the algorithm. So we're back where we're at the point where we define the algorithm, and here's the algorithm with a random initialization. So this initialization helps us to essentially prove things. And what you see is now something that has the flavor of a neural network, of a recurrent neural network. So these are vectors, n-dimensional vectors. So first of all, you multiply a matrix A, which is defined by that. So if J is a rotational invariant matrix, then A is also a rotational invariant matrix. So you have this specific matrix. You multiply it by this vector. You get a new vector gamma, and this vector gamma is fed into a nonlinear transfer function, pointwise, and nicely it contains hyperbolic tangents, sigmoidal functions. It has very much a flavor of a neural network dynamics over time, where you have the same matrix in every step. It's unlike the deep neural network, where we have different matrices at each level in the deep network. It's always the same matrix A. There's a bit of pre-computed things that you have to do a nonlinear equation, and if you want to run this algorithm on a specific matrix A, you replace all these R transforms and things by the empirical counterpart. So you start by computing the matrix and then do an eigenvalue eigenvector decomposition and replace everything by its empirical counterpart. So you can apply that to a specific problem without actually knowing what the ensemble is. You just assume that the eigenvectors are sort of in general position. So this is this kind of dynamics that we have to study. And so is the question, what can we do? And so we've been looking at a slightly more general type of dynamics. So we introduce some function, arbitrary function f of these vectors, which will be related then later to this hyperbolic tangent and so on, and assume that A is a rotational invariant random matrix. So we use a technique that was popular in the statistical mechanics of disordered systems. It's the so-called generating functional technique. So the idea is to represent the trajectories of the dynamics within a partition function. So we have some kind of things where we integrate over all the variables, obeying the constraints essentially of the dynamics. So that means we put in the dynamics into delta functions such that we run only over those trajectories at each time t that obeys the dynamics. And so we have the random matrix within a delta function here. And what we're interested in is in the generating functional. That's not really a function, it's discrete time here. Originally, the method was used for continuous time processes like Langevin dynamics and so on, and so forth, introduced by Martin, Sidja, and Rose. But then later also applied a lot to soft spin dynamics with random coupling matrices by Sompolinsky and Sibelius. And I think there was already on the first day some comment on a paper of Sompolinsky and Crisanti, actually, who derived results by using this dynamical function. In this case, A was a non-symmetric Gaussian matrix. So this is this kind of background, and we have these external variables. So if you would be able to compute the expectation over E over the ensemble A, and do derivatives with respect to Li, you would get the statistics, expectations of gamma I, and so on and so forth. So this is this kind of idea. And so, in a nutshell, we have a paper in 2016 that explains all the gory details of this approach. I think what the new thing of this paper is essentially we extended this method to rotational invariant ensembles. So what we are doing is replace this delta function by its Fourier representation, and then you would get expressions like that, for which you have to take the expectation over A, and this can be done for a rotational invariant system in the large n limit. And then we will find, after taking the average, of course, the disordered system is no longer disordered. It's kind of a homogeneous system. And so the resulting non-random model can, it has still interactions, but the interactions are by order parameters, which become self-averaging in the limit n to infinity. And so you deal with these order parameters by saddle point integration. But these order parameters that sort of are introduced in order to decouple the degrees of freedom are now coupling the times. So the degrees of freedom become independent in the large n limit, but you get couplings over time. And so I use the word exact here, so this is a kind of community thing. So if you come from statistical physics, you say this is an exact result, but then it's not rigorous because there's a lot of steps that would have to be cleaned up, and so there might be other techniques that would help to get the same kind of things, but I'm pretty sure that it's exact. So what we do is now we take the limit n to infinity, but keep the number of steps that we do in the iteration finite. So we will actually see that plays a role for large and concrete matrices. So this is the result that we get in general. So we get essentially an effective dynamics for a single node. So the dynamics of a single node can be described by the following equation. So this is the node equation, so we have to pass this field gamma to obtain the gamma tilde. And then the gamma tilde, so the update of gamma is via interactions over time, so the G hat matrix, and from outside there is a Gaussian noise field acting on it. So you might say, well, this is actually, yeah, we say you apply a random matrix to a vector and look at the resulting components, maybe Gaussian, but by the fact that this is a symmetric matrix, actually there will be, this is sort of the incoherent interaction with the rest of the system, but the state of the system at time t is will influence the state of, by interactions with other variables, is sort of influencing the state of the system at a later time. And since the interactions are weak, what plays a role is the susceptibility matrix of the problem. So this is this kind of picture that we have, which has kind of an intuitive understanding, but unfortunately the details are very complicated. Again, we have the R transform, and now we take the power series expansion of this function and insert instead the matrix G, and the matrix G is this T by T matrix. And it's even worse when we look at the covariance function of the Gaussian process that involves the so-called free cumulants. And here is this is again the covariance of the gamma tilde process. So essentially, there's not much we can do. And many years ago, I had actually suggested to use Monte Carlo sampling for these kind of dynamics, and it can be done if you want to look at essentially it was in the days of neural networks. Yeah, but it's ugly, so we could rather stop. But for the specific choice that we have here and the specific matrix, we get a large simplification. Yes. So it's much simpler. In this case, well, we have this one thing, move through a nonlinear function f with this kind of thing, and the gamma field has just Gaussian noise, and all these interactions over time have completely disappeared. So that's the very nice result, and also the covariance function of this Gaussian process can be computed iteratively in terms of very simple functions, and you can do that essentially numerically. So with this kind of thing, also depending on the specific random initial condition with the correct variance, we get a very much simplified result. And I hope I have time to get a flavor why this actually simplifies. And so the interesting thing is now having this simplified single variable dynamics for the large n limit, we can study so how close to trajectories. This is the same trajectory at time t and time s. So will they get close to each other in the limit n to infinity? And what we find actually, we get under some technical conditions, and the funny technical conditions is known in the spin glass world as the D'Almeida-Thouless line. So it plays also a role here in the dynamics. We find that we get convergence from a random initial condition, and we can actually calculate explicitly the rate of condition, so the rate of convergence. So this is a result that we have, and we can compare it with simulations of a concrete random matrix. So this is a specific choice that we have that is rotationally invariant. We call it a two-layer Hopfield model because it has this outer product structure, and each factor is the product of two Gaussian matrices. For example, we gave examples in our paper. What kind of more examples? What kind of J's we can easily construct. And so here's the difference between what we get out of the algorithm, so the empirical covariance, and this is the computed covariance from the theory, and so it's the quadratic difference on the log scale. And you see it's pretty close for the simulation for 10 to the 4, and this is not an average over many realizations of the random matrix. So this is one fixed random matrix. So it's not an average result, and so suggesting this is really something. We get self-averaging properties in the limit n to infinity. So for a large matrix, that seems to describe very well the iteration over let's say 10 time steps. So what happens if we go to larger times and look at the asymptotic convergence? You see already so the difference between of our result for two different time steps. How close are those? And you see we're already at very, very small things, and this red line is given by the theory that we computed, and the blue lines come out of simulations. And we see when we approach the critical temperature of the problem here, that would be the Almeida-Thouless line. We see, well, okay, for the first few iterations it's okay, but then this bends slightly over. And of course, in this region we are already, so we get slower and slower convergence as we approach the critical point. But it should also be interesting to see if we are already at these very small distances. We are in a region where the time is too large that our self-averaging properties hold. So I think in this case, the limit n to infinity and t large is not anymore valid here, and we would have to possibly think about what happens if we discuss the product of random matrices and possibly look at the largest eigenvalue or something like that. So we would need a different theory for this kind of region. And here's an example of a case where we actually do two realizations, and so this is what we would get for the decay from the theory. So yes, well, it works pretty well, but we have here. So we have two realizations, one this line and one that line. Well, actually, asymptotically, the slope is the same, so possibly we can get some theory also for very large times, but it's only the initial decay which remains the same, but the decay for very large times is different. But I think from an algorithmic point of view, we are already quite good in terms of convergence here. And there's also a comparison here with a different algorithm that have been discussed in a previous paper, showing that actually we are faster, at least in the beginning, but I don't know, in the region 10 to the minus 15, possibly we're not really interested in that region from a practical point of view. So, right, quite in time, so I don't have to really hurry. And so there's the question. I said, look, in general, the dynamics of such a problem with random matrix couplings looks terribly ugly. There are all kinds of temporal dependencies, but we can sort of look at at the results and try to get a little bit of an understanding. And the way we initialize the algorithm, and a few details that help us actually to get the analysis a bit streamlined with a few little changes. Essentially in the algorithm, it is easy to see that if we linearize the dynamics, so we look at, so we have to compute that how does the iteration at time t depend on time t minus 1, we see it's a product of two matrices, A, which is the original random matrix A, which is rotationally invariant, and a diagonal matrix. The interesting observation is this expectation propagation method says essentially that the normalized trace of the two matrices are actually zero. That's something that comes out of the EP condition. So we have this type of thing. And if we could assume freeness between A and B, then essentially we would get that the subscriptability, so how does gamma I at time t depend on gamma I on the previous time steps, assume self-averaging and freeness. I think we can get the self-averaging also from freeness, that would go to zero. So that explains that there should be no self-interactions over time, and we get the nice result. The other thing is,
Manfred, is that
yes, please.
is that a result for large differences t and t primed, or for any?
For any.
For any.
Yeah.
Yeah, that's
No
the,
memory.
But still you have to do the limit n to infinity.
for all time,
Okay.
it kills me memory.
And the other thing is, if we want to understand how the system relaxes, we can't do that now completely, but we could study a small random perturbation away from the fixed point and use this result. And if we assume again this kind of structure, we get this kind of product of random matrices together with freeness, we would get the asymptotic decay, the decay over time for the decay of this perturbation is given by such a result. And if you compare with our previous insert all these results for random matrices, we get this is the exact decay that we got out of the dynamical functional method. So our hope is that at least if we want to understand parts of the asymptotics, that it will be enough to stick to freeness arguments rather than to detailed rotationally invariant kind of things, and we hope that maybe our results could be more robust than for these specific ensembles. Another hint that this might be more robust is if we make a little detour from the random orthogonal ensemble, but introduce another ensemble where we have another orthogonal matrix O tilde here rather than the random rotation. And that is given by some things related to Hadamard matrices. So in this case, we are assuming that these orthogonal matrices are given by Hadamard matrix multiplied by a binary matrix. And so in the middle, we also assume binary elements. And so these Hadamard matrices make essentially O tilde also orthogonal, but it's not a general direction, but these elements are plus minus 1 over square root of n. So it's a specific type of thing that is not sort of with high probability belonging to an orthogonal ensemble. So we just take this. And of course, we can also, for these kind of matrices, compute R transforms and so on and so forth, and insert into our results and compare with the computations with the covariance matrices over time that we did. And also you see on this level we get an excellent agreement. So it seems to be more robust and the same thing, similar things for the asymptotic decay of our dynamics. So this is the brief outlook that we have. Of course, we started with a very simple thing like an Ising model with a random coupling matrix, not really a data model, but I think we understand a little bit now how to extend this to other problems with data models fit in. And of course, then we would have to compare things with real data, of course. We are not generating this randomness, but the randomness would come from real data. And then, of course, another problem from the theoretical point of view is we often would think that these matrices are results of learning, of adaptation by some whatever maximum likelihood method for getting the matrices. So it's a question that the ensembles would evolve over learning time, and the question is, can we in some sense deal with that? That's one of the future problems, and here's a list of publications that we have. So the first one explains essentially dynamical functional for rotational invariant matrices, 2016. This thing is how to simplify the EP method using free probability, and some Isaac 2018, and we have also an archive now where we have all these details about the dynamics. And with this, I would like to thank you for your interest, and thank you.
Now we obviously have time for questions.
I'm a little bit puzzled about this memory-free thing. This is normally something if you have totally asymmetric interactions.
Yes, indeed.
And this is what you assume here, is that?
No, it's not symmetric. It's a symmetric matrix. So this is why it came as a surprise.
Okay. And how do we understand that now?
We understand that actually from arguing that the matrices have, that the matrices involve, essentially if you compute the substitutability matrix, you get a product of this A matrix and a diagonal matrix, and it turns out that they are sort of, on average zero. An average, when I mean by the normalized trace. And now if I can assume, and this is of course one of the assumptions, because the diagonal D and A are not independent, but we still hope that freeness holds at A and B. Then, of course, if we compute this kind of object, we have a product of these matrices, and if they're all free, so we know that the phi, the trace of this kind of guy, would be zero by freeness. But then we can also make with a little longer computation of the argument that this is actually, that holds individually. So this is, on average, this is zero, but then we can argue. I think you would say self-averaging is possibly okay from a physicist's point of view. So they're zero on average, the normalized trace is zero, and they also should be individually zero. So that's our kind of argument.
That's a strong additional constraint, right?
What do you say to constraint?
If the trace is zero or individual elements is
No,
zero.
you prove what?
We can prove this under freeness that we also get point-wise zero. So that is our kind of argument. And then we hope that we might get the whole story completely from freeness, but this is something we want to work on using other techniques that are there on the market, not dynamical functional theory. That's the only thing I can say so far. It was surprising, but yeah.
In your numerical work, are you using the R transform for the ensemble or the empirical version of it?
The empirical one.
And how do you construct that exactly? So
I don't have it here, but I mean, you saw with the green function, right?
Yeah.
I mean, you diagonalize your matrix, you get your empirical eigenvalues, you get your empirical green function, and then compute, rather than writing down the expected, the real green function, you take its empirical counterpart and set it into the definition of.
But you have
the
to you have to
transform.
functionally invert that thing.
Yes, but
So
this
this
is
is the
something
hard
you
part
do
somehow.
before. This is something you do before the algorithm starts.
Mhm.
And so you have to do.
So you build a big table or something that's telling you the inverse, or
No,
no,
actually
It's
functioning.
referring inverse of function.
Yeah.
Yeah.
Digit inverse function. Inverse of digit. You don't need
Okay,
to
you say.
this immersion because
Okay.
No, but you have to
it's an
solve
iterative algorithm. You solve
have to
this
solve this
immersion
at nonlinear-
iteratively.
Yeah.
a nonlinear equation. Not many, but only one, essentially.
Okay.
Just to understand, green function is what the other protocol stands for.
Yes, exactly.
Is there any relation with of this dynamic analysis and the state evolution of A and P?
Not yet. I mean, there are similarities
There are
because
similarities.
because people who analysis density evolution by rigorous method, they also obtain Gaussians.
Yes.
But I mean, in our case, we have joint Gaussians over all time. I think that's missing in their analysis, and that's why we can get a little bit more. But we hope that we can use these conditioning techniques to get back these results.
But you can use this is a generalization of state evolution. If you apply this method in this data model, instead of this convergence, so you get a general state evolution for different times, so you know all how the dynamics behaves. So state evolution only refers to time t equals t prime is equal to t. So it's only because
So
you
this
look at
gives
the
you the
variances,
full-
dynamics of the variances, state
state
evolution.
evolution, I mean, it relates t and t minus 1.
Yes,
One
yes.
step.
And that gives you distributions of the entire trajectory of one node.
Yeah.
That's what you get out of that. So it's a joint Gaussian process in this case,
Okay.
and with an explicit way of computing the covariance iteratively. So you can also compute, yeah.
Also, another question: is there any chance? Because one thing that is still kind of missing. I mean, in A and P, some people, I think Alison Fletcher, have some results very complicated. Would be really nice for this type of algorithms is to have not so large, so the fluctuation. You know, say state evolution tells you, or this tells you what happens with the trajectory in the say in the limit, right? What we would like to have is the distribution is how this trajectory fluctuates for n large in terms of order of one, I don't know, 1 over n variance, 1 over square root of n, some sort of central limit theorem of the trajectory.
Yeah.
Because
well,
this is what people have done in analyzing LDPC codes. For example, for belief propagation and sparse graphs, there are techniques that can give you the finite length scaling of the. So basically, density evolution tells you in the infinite graph limit.
yes.
But then you can actually scale this result and have a finite length.
I mean, I could say yes in principle if you say okay, what we are doing essentially we're basing this analysis on saddle point methods, and then we would have to go to include fluctuations around the set. I think it's technically possible to write down something. I don't know if it's if it's too complicated to get anything reasonable out
There
of
is
it.
one big misunderstanding in the community of this AMP and so on. State evolutions refers, yes, the dynamics of this variance of you said previous time.
Yeah.
So we know that the algorithm is, if it is solved, it is consistent with this replica result. So the purpose of all this state evolution, in fact, is somehow misleading to me, because we have to understand whether we can solve this equation. It's a middle step. We have to understand how it converges. So I think this is the right question in this community should be whether this, yes, you get state evolution, very excellent, but whether this state evolution is convergent. If it does not converge, if it converges, you know that this my MMSE is same as replica result.
a state evolution, well, let's say, maybe, I don't know, to have people interested, or should we move on?
I think we should.